All right, then let's begin. Okay, so far we have talked about gravity, and that is one of the fundamental forces that is present in the Earth. And of course, we have seen how, as geophysicists, we can use gravity for our own purposes of exploration. Uh, So today we are going to look at another fundamental force today and for few other days, and we are going to see, and that is magnetism, of course.
So
Yeah,
I had a doubt in the last lecture,
yeah. Tell me.
that isostacy one.
Yeah.
So you said the upliftment and the erosion process occur simultaneously in a cycle.
Yes. True.
So how will that processes occur in the Pratt's model of isostacy, as there is no um, below the crustal layer, there is no landmass.
So I mean, why the? I mean, these are Pratt's model or Airy's model, where they are independent of that. I mean, both of them actually happen. Uh, I mean, erosion is not essentially dependent on those models, right? Erosion is dependent on the surface processes that act on the land masses, and they will anyway erode, right? So in either of the cases, you actually create a mass imbalance, right, and hence you have uplift, right? So mass imbalance in either of the models, what is actually achieved is the mass balance, right? That equilibrium is achieved. Yeah, either by uh, making some roots underneath, or distributing the density, right? So that is what happens in both the models. But then if you disturb that particular equilibrium by introducing erosion and by removing some landmass, it will have an uplift irrespective of the model. Okay.
Okay, sir.
Anything else? Sorry, I forgot to ask you if you had any doubt. Yeah, let's solve your doubts first, then we can proceed. Anything else? All right. Shall we then uh, continue with our lecture? Okay. So magnetism. Okay. So as you know, this is also one of the fundamental forces that resides in the Earth. Okay. And how I typically draw a magnetic field, and this is very much known to you. So I'm drawing a bar magnet which has a north pole, has a south pole, and then of course I have these beautiful field lines. These field lines are nothing but the equipotential surfaces as well. This is how you have all, I think, done experiments in your undergraduate physics lab, or during your higher secondary, where you took a bar magnet and then you have put some needles on a piece of paper, and you could see that they actually align perfectly along the field lines. I'm sure you have done such experiments in your life, so you know everything about how field lines work and everything. Now, a few things, some very basic things I just wish to recap, and then we will proceed with how it is applicable for our own purposes. So, one of the things, if you compare magnetism with gravity, so what you can immediately see, that the magnetic fields are not central. It doesn't really start up like that happens in case of gravity. It's not centralized, so it has like a north pole, it has a south pole. Okay, so the first difference from gravity is magnetic fields are are not central. Okay, let's just write down not central. And the direction, of course, vary with azimuth. Okay, the direction of these field lines vary with azimuth. Now, so if I think that there are two poles, P1 and P2, okay, so the force acting between P1 and P2 is described by Coulomb's law, for magnetic poles, where it is written Fr is equals to K P1 P2 by R square where P1 and P2 are the field strength. K is a constant, of course, which is a dimensionless quantity, and R is the distance between these two poles. Okay. Now, one of the things that you have to remember, although we invoke the concept, I mean, we will use the concept of single monopole. I mean, the way it is drawn, the equation is written as if P1 and P2 can exist on their own, right? As if P1 and P2 exists on their own. So we can call them as monopoles, right? But for all practical purposes, for the magnetism that we know, monopoles do not exist in nature. Okay, but for our own purposes, for our own convenience, if you like, we consider monopoles for our calculations, but they do not really exist in nature. So, what do I mean by that? That if I keep on breaking this magnet, okay, suppose I break this magnet, I will break it into two pieces. Okay, and then each of this magnet will have a north pole and a south pole. Okay, and then if I again further break it down, they will also have north pole, south poles. Yeah, if I further break it down, I will never be able to single out a north pole or single out a south pole. Any magnet that exists in nature will have its own north pole and its south pole, right? So monopoles, although we will use them in theory and use them for many calculations, they do not really exist in nature. And this is purely for our own convenience, why we actually invoke the concept of magnetic monopole in our life. Okay. Now, pole strength has a unit of over dyne centimeter. Okay. And this is what we call as Gauss, I guess. Just a moment. Yeah, this is what we call. So this is pole strength root over dyne per centimeter. Now, if I essentially put that in this equation, what I will find that the magnetic field then will have a unit. So this magnetic field will have a unit of, that will be root over dyne uh, multiplied by centimeter to the power -1. Okay, and this particular unit is called Gauss. Okay, and there is also a smaller unit of it. So 1 gamma. So the smaller unit is called gamma, is 10 to the power -5 Gauss. Okay. Right. Now, earlier people used to think that K is actually dimensionless, but now with modern understanding and we know that K is not dimensionless, and in SI units, K is actually thought to be mu 0 by 4 pi, okay, where mu 0 is called the permeability constant of a media, okay. My magnetic permeability. What do I mean by magnetic permeability? I will discuss later on. Okay, the mu 0 is here called the permeability constant. Okay, and this is the value of K then becomes is around 4 pi into 10 to the power minus 7 Henry per meter. Okay, and 1 Henry is equals to 1 kg meter square. Now A is ampere, okay? Because you know magnetic field and electric fields are pretty much run hand in hand, okay? Now, like we have established for gravity, we have talked about gravitational potential. Similarly, we have magnetic potential. Or the potential of the magnetic field. And this is essentially the work done to bring, move a particular monopole for a particular distance, and that is expressed as W, and this R to infinity, BdR, where B is essentially the magnetic field, okay? And the equation comes as mu 0, P is the pole strength by 4 pi R. Okay. So R is the distance that the monopole travels. P is the strength of the pole, of course, and this is how we define magnetic potential. Okay. Now let us say we have a very small dipole, okay? Because we said in nature, dipole is the smallest that you can go. Suppose, let us say the north pole is designated as P plus, the south pole is designated as P minus. Okay, and we wish to find out the potential at a point, say x, okay, and this distance, let us call it as R plus. This distance, let us call it as R minus. From the middle of the dipole, okay, from exactly the middle of the dipole, let us say this distance is small r. Okay. The total length of the dipole, let us be it d, then this is d by 2. This is also d by 2, okay, this distance. Now, this angle, perhaps, let us assign it as theta. So, at this particular point, the magnetic field due to this dipole, and let us say that has a direction in this, any arbitrary direction, is B, and we can simply resolve this B into two components. One we can call as BR, and perpendicular component as d theta. Okay. Now, if I want to consider, I want to understand the magnetic potential for this particular dipole. Okay. So the work done, okay, so the work done W will be equals to, using the formula that we have just wrote down, mu 0 p by 4 pi 1 by r plus minus 1 by r minus. Okay, so this is the potential by the by the north pole, if I say the positive pole, minus the potential by the south pole or the negative pole, because they actually work opposite to each other. Okay, now if I simplify this one, wow, we can write down mu 0 p by 4 pi r plus r minus minus r plus. Okay. Now let us assume that this d, the value of d, is way lesser than r. Okay. Because we are really considering a very small dipole. Okay. So then r plus can be expressed as, it is nearby r minus d by 2 cos theta. Similarly, r minus can be written as, not exactly equal, but very near equal, r plus d by 2 cos theta. Okay. Now, if I substitute the value of r plus and r minus and express that in terms of r and d, okay, this particular, so r minus minus r plus, that becomes, that is the above term here, that becomes d by 2 so you can write, this becomes d by 2 cos theta, d by 2 cos theta, that means around d cos theta. Okay, d cos theta. And then r plus r minus, this becomes, very close to r square. So now if I replace that here, what I will find out, W is equals to then mu 0 p by 4 pi d cos theta by r square. Okay. Now, there is one very important term here, that is what I wish to introduce to you, and that is the whole reason we have done this whole derivation. And this brings us to one of the most fundamental quantity that we are going to use in our course, and that is PD. This is the multiplication of the pole strength multiplied by the distance between the two poles, that is the length of the dipole, and that is we call as small m, or this is also called magnetic moment. Okay, magnetic moment. Okay, so that means it's the pole strength of, p plus and p minus, although they are like opposite in direction to each other, but their value, the magnitude of them must be the same. Okay, and the distance between these two poles in a particular dipole, if I multiply that, the quantity that I get is called magnetic moment. Okay, so if I kind of simplify this in terms of, if I replace PD with M, what I can write down, mu 0 by 4 pi. This is a constant, of course, m cos theta by r square. Okay. This is a very important derivation that you must remember. Okay. Now, and this is also another very important quantity that we are going to use in our throughout our course. Now, let us say I have a magnetic field which is directed like this, okay? B, an external magnetic field. On that external magnetic field, I have now placed a magnetic dipole arbitrarily. Okay. So this is P plus, this is P minus. And suppose at this particular moment in time, this is making an angle theta with the direction of the magnetic field. Okay. With the direction of the magnetic field means the direction of the field lines. Okay. The local field lines. So this distance is d. And so this, if this is theta, then this is d sine theta. Now, can you tell me, if I keep a magnetic dipole, okay, under the influence of magnetic field making an angle theta, what would this particular magnetic dipole would try to do from your experience?
Rotate.
Rotate. It will try to align itself along the magnetic field, right? Is that right or not? Okay. So if it does, of course, it will feel some sort of torque, right? Let us say then, because this is like this, so the force that will be faced here is the strength of the magnetic field multiplied by pole strength. And similarly, the same force will be felt here, okay? So this is the direction of the force. F is equals to Bp. So the torque, experienced by this magnetic pole will be F into d sine theta. You know about this fundamental physics equation of mechanics, okay? F into d sine theta. So now I can further replace F with Bp, right? So I can write P d B sine theta. Okay. Now P multiplied by d is what? We have just said. What is P multiplied by d?
And magnetic moment.
That is magnetic moment, right? So mb sine theta. Okay. Or I can write down the torque experienced by this particular dipole will be, is a cross product of m and b. Okay. So tau is m and cross product of b. Right. Vector multiplication. Okay. So that is the force experienced by, that is the torque experienced by this particular dipole if I keep it in a inside any external magnetic field. That is important to know. Now, if I look at a rock, because that is what we are, primarily interested in. If I look at a piece of rock, okay. Now, the way I can imagine this particular rock is that it has several magnetic moments, which are which can be directed in a particular direction, or it can be absolutely random. Okay? Which can be aligned, which might not be aligned. Understand? So these are all individual magnetic moments. They could be of same strength, they might not be of same strength as well. Okay, but the moral of the story is that we will now assume a piece of rock or a piece of mineral when we discuss magnetism as an aggregation of several magnetic moments, okay, which might or might not be aligned. Okay, so here I'm going to introduce you to another term which I call as magnetization. And magnetization is defined as M is a summation of all the magnetic moments divided by the volume of that piece of rock or the volume of that piece of mineral. Okay, and this is what we call as magnetization. Now you can imagine, if I find a rock where these magnetic moments, are extremely aligned to a particular direction. So now tell me, from your understanding of magnetic moment and common sense, if I consider rock 1 and then if I consider rock 2, in one it is absolutely aligned or very much aligned, and the second one, in the second situation, the rock is kind of, the magnetic moments are randomly distributed. In which one you have a strong magnetization?
One.
In one, right? So this one will have a very strong magnetization, but in case 2, of course, the magnetization will be weaker. Now what I can do though, that I can subject this piece of rock, yeah, I can subject this piece of rock under external magnetic field, and I can force these magnetic moments to actually align themselves. Okay, so I can kind of bring up a situation where, these magnetic moments start to align themselves. Okay, now remember that while we are talking about this realignment, we are not essentially talking about the realignment of the mineral grains. Okay, the mineral grains still remain the way they were oriented. It's only the magnetic moments that are getting reoriented. Okay, so it's not that the physical orientation of the mineral grains are being changed, okay, under external magnetic field. If you want to change the physical orientation of the mineral grains, of course you have to apply mechanical force, right? But if, because of course that the rocks are interlocked, the mineral grains are interlocked with each other, so the texture does not allow them to essentially move freely under the influence of external magnetic field. Okay, it's uh, it's the magnetic moments that realign themselves. Okay, so of course if I subject that randomly oriented magnetic the rock with randomly oriented magnetic moment to an external magnetic field, the magnetic moments can get bit more aligned and the value of M can increase, right? Now, on what this particular phenomena, this further realignment is possible, depends on this particular equation, and that is what we call as M equals to KH. Okay, where M is the magnetization H is the external magnetic field. Do you know what does this K mean? What is the name of this term K? Can someone tell me? Do you know what is K? Anyone? If you have studied before. I'm sure you have studied this one before. Can someone tell me? What is K?
Sir, is it susceptibility magnet?
Susceptibility, absolutely. So K is called magnetic susceptibility. So in other term, K is actually M by H, okay? So what does that mean? That if I have a rock which has low susceptibility, let us try to understand this physically as well, okay? If I have a rock which has low susceptibility, and if I subject it to a particular field strength, okay, the magnetization will not be great, okay. If the susceptibility is higher, that means if even if that rock is randomly oriented, the magnetic moments are randomly oriented, if I subject that rock under external magnetic field, what would happen to that rock? It will acquire more magnetization, okay. Does it make sense? Do you understand this point? If I have a rock which is having lower magnetic susceptibility, if I if I allow, if I subject that to external magnetic field, it will the magnetic moments will not be very much aligned, even if the field strength is very high, even if this H is very high. If I have a low magnetic susceptibility, the acquired magnetization will not be great, okay. But if the susceptibility is higher, okay, then if I subject it under external magnetic field, most of the magnetic moments will try to align themselves, okay. So if I think of, say for example, iron, and if I keep iron under if I pass electricity through iron, or if I rub iron against a magnet, against a permanent magnet for some time, I can acquire magnetization in that particular piece of iron, okay. So what does that mean? That iron has very high susceptibility, okay. Iron has very high susceptibility. In other words, we can say that this is another way of looking at it. Suppose I have a magnetic moment, okay, and I am applying external field strength to it, okay, which is oriented maybe at a perpendicular or maybe at a high angle with the magnetic moment, so higher susceptibility means that it doesn't have enough strength, it can essentially very easily, it doesn't have enough resistance, it very easily aligns itself with external magnetic field, okay. But higher susceptibility means this particular magnetic field is extremely stubborn, okay. It's very difficult to put them under the influence of external magnetic field. They will not rotate, they will be where they are, okay, or rotate a little bit. So which is very, the analogy is very similar to our human society as well. Some students do listen to the teachers and try to I'm not saying which one is good, which one is bad. It both have their own good and bads, but some gets influenced easily, some do not, okay. But it's exactly like that, some minerals have magnetic susceptibility which are higher, and as a result they align themselves very easily. Now if I look at our common rocks, okay, let us first look at the common minerals, okay, and look at their magnetic susceptibility. Let me just draw it first, huh? This is magnetic susceptibility. Let us say this is K0, okay? I'm plotting it in log scale. So 0.01, 0.1, 1, let's say 5, okay? Not exactly log scale, but that should solve our purpose. Now, if I look at quartz, okay, this is quartz. You know what is the composition of quartz? Can someone tell me?
SiO2.
SiO2, silicon dioxide. But you observe that quartz has a negative susceptibility. What does, and the value is around minus 1.5 into 10 to the power minus 5. Sorry, this is magnetic susceptibility in SI units. Okay. Now minus 1.5 into 10 to the power minus 5. That means the susceptibility is extremely low. Okay, and it is negative. What does negative means? That, you know, so let us first understand what does low mean. Low means it has very low magnetic susceptibility. You will not be able to move those magnetic moments. They are extremely randomly oriented. Okay, you will not be able to move them at all. They are extremely stubborn as well. But then if you are able to move one or two of them, okay, a little bit, they will move opposite to the direction of the external magnetic field. So if the magnetic field is directed northward, the magnetic moments, whatever gets aligned little bit, they will get aligned towards south. Okay. So that means the teacher is asking you, to go to, follow a line, along going towards hostel. You will not go to the hostel. You will just move around the campus. You will not follow a line. But maybe one or two of you want to align themselves, but they will run towards main gate. Do you understand my analogy? Yeah. The teacher being here, the external magnetic field. Okay. So that is how quartz behaves. Similarly, you have calcite, which is also very low magnetic susceptibility. You can find out the numbers from Lowry's book, no problem. This is also around 1 minus 1.4 into 10 to the power minus 5. Okay, this is calcite. What is the chemical formula for calcite?
CaCO3.
What is the other? Uh, carbonate that we find in nature? Carbonate mineral. What is the other carbonate mineral that we find in nature? One is calcite, the other one is another very famous carbonate mineral. Tell me, guys. Dolomite, CaMgCO3 whole twice, okay? That also behaves very similar to calcite in terms of magnetism. Now, this is calcite, another rock forming mineral that also has a lower magnetic susceptibility, and the magnetic susceptibility is negative. Okay. Now, let us look at pyrite. What is pyrite? Can someone tell me? You don't have to tell me exact formula, but you can tell me about its general composition. What does pyrite contain?
Iron sulfides.
Iron sulfide. Very good. Now, pyrite also has lower susceptibility, around 0.0015. Okay, but you can see this is positive, right? This is positive. Now, this is sulfide, pyrite, FeS2, I guess. Then you have another. Now let us look at some oxides. This hematite. What is the chemical formula for hematite? Can someone tell me? What is hematite?
Fe2O3.
Fe2O3. Hematite is also, as you can see here, it is positive magnetic susceptibility. It's around 0.0065. Then, if I look at pyrrhotite, positive high susceptibility 1.5, and then of course magnetite, very high magnetic susceptibility around 6. Okay. Very high magnetic susceptibility. This is pyrrhotite and this is magnetite. Pyrrhotite and magnetite. Okay. Magnetite is a Fe3O4. Pyrrhotite is a iron oxide with hydrous minerals in it. Okay. Now, this is how the minerals behave, and then you can find out for all rock forming minerals how they are, which one has higher susceptibility, which one has lower susceptibility. Now, of course, if I now look at rocks, the rocks that contain such minerals, say, what do I mean by that? So, if I have these magnetite or hematite, even present in a particular rock in trace amount, not in great amount, but maybe few grains, it can actually enhance the magnetic susceptibility to a greater extent. Okay. Now, if I look at how the rocks behave, so around 10 to the power minus 5, to the power minus 4, minus 3, minus 2, and so on. Okay. So this is where dolomite sits. Dolomite, so limestone sits. Limestone means calcium carbonate. This is where sandstone sits. This is where shell is there. Okay. Because they are primarily, does contain silica. Okay, so it doesn't really contain a lot of magnetites or hematites. But then, if I look at the igneous rocks, these are my sedimentary rocks. If I look at the igneous rocks, of course, they are sitting here. So maybe gabbro, basalt, granite, gabbro and basalt are more or less at the similar space. Okay, so you can see the bulk susceptibility, and this is what we call as bulk susceptibility, the total susceptibility of a rock. It's not of the individual mineral grains, it is the total susceptibility of the rock, depends on its mineral constituent. And of course, if I have these oxides like hematite, magnetite, pyrrhotite present in a rock, which is more common in igneous rocks, of course, the susceptibility is way higher. Okay. Now, what you need to also remember, and this is very fundamental, that this oxide series, this oxide solution, solid solution series, you know what is solid solution? You have already studied. Yes or no?
Yes, sir.
Okay, very good. So this oxide solid solution series also I suppose you have studied, and it has 3 end members: rutile, wustite. This is a German U with 2 dots means umlaut. Okay, wustite, and then here I have hematite. Okay. which is, so rutile is TiO2, titanium oxide. Woostite is ferrous oxide, FeO, and then hematite is Fe2O3. And we can have, and then I have, within rutile and woostite, I have solid solutions, and I will write down uh, three specific names here. Why, I will explain in a moment. One is called ulvospinel, and that is Fe2TiO4. Then the second one I will write down as ilmenite, and that is FeTiO3. You can see as we are moving towards rutile, the amount of titanium is increasing in the crystal structure. And then ilmenorutile, rutile or rutile, it's named both ways, FeTi2O5. Okay, and then I will have a solid solution between TiO2 and rutile and hematite as well, and that is what we call as pseudobrookite. Have you read this solid solution series already or not?
So this one not.
No. Okay. So this is iron oxide solid solution series, as famously known. So now you also have solid solution between ilmenorutile and pseudobrookite. You also have a solid solution. You also have a solid solution between ilmenite and hematite. And then you can have a solid solution between woostite and hematite, and somewhere in the middle I will have magnetite, which is Fe3O4. This is magnetite. And then I can also have a solid solution between ulvospinel and magnetite. Okay. Now this particular solid solution series, I'll highlight the two most important solid solution series for our purposes. One is this one. This is the solid solution between hematite and ilmenite, and this is called titanohematite series. Okay, this is called titanohematite solid solution series. And this is the solid solution between ulvospinel and magnetite. This is what we call as titanomagnetite solid solution series. Titanomagnetite solid solution series. Okay. Now, the igneous rocks that we have just talked about, okay, the igneous rocks that we have just talked about, they can contain all these things, all these oxides, but the most commonly occurring oxides are belong to the titanohematite series or belong to the titanomagnetite series, and that essentially is responsible for the bulk susceptibility that you observe in case of that you observe in these in these rocks. Okay, so that is what you have to remember. Now, I'll quickly introduce you then to, so you can see that we have classified rocks, we have classified minerals based on their susceptibility in basically while we were drawing that diagram into three categories. One is low, K low and negative. The other one is K low but positive. And the third one is K high and positive, right? That is what we have seen. Now, K low and negative, this is what we call as the diamagnetic minerals. K low and positive, this is paramagnetic. K high and positive, you see, this is ferromagnetic. Okay. So if I just simply draw a diagram, you know, so here will be your paramagnetism K greater than 0, but of course this is not very high. Okay. And K less than 0, this will be your diamagnetic. Okay. Right. Now, let's just then, so you already know about how much time do we have? 7 minutes. Okay. Now, there is another important thing that I want to introduce. Okay. So generally, diamagnetism is around, the susceptibilities are in the range of 10 to the power minus 6, but negative SI units around for diamagnetic minus 10 to the power minus 6 SI units. Okay. For paramagnetic, it's the similar value, but at the positive. Okay. Similar value at the positive. And of course, for ferromagnetics, it is way higher, that like we have already drawn. Now, there is another important concept which we call as Curie temperature. Yeah. So what is generally seen in case of ferromagnetic minerals, what is generally seen, that the ferromagnetism is generally so suppose I am drawing susceptibility versus temperature. Okay. So suppose I am looking at a mineral which is ferromagnetic, so it has a fairly high magnetism, and I am increasing the temperature. And after the temperature, what I see a sudden drop in my bulk susceptibility. Okay. I see a very sudden drop in my bulk susceptibility. And this particular temperature is called Curie temperature. Okay. So magnetite has a Curie temperature in the range of around 575, 578 degrees centigrade. It depends on how much titanium is in the system, because we have already seen that you can have pure magnetite, but you can also have this whole solid solution series. So depending on the amount of titanium present in the crystal structure, the Curie temperature actually changes. Okay. Now, for hematite, it has a slightly higher Curie temperature. It's around 675 degrees centigrade. But there also you have to remember, it depends on how much titanium is present. So you have kind of a range of around 50 to 70 degrees centigrade, and you do see like a spectrum of you do see like a spectrum uh, of Curie temperatures depending on or in that particular solid solution series where it actually belongs. Okay. In case of paramagnetic minerals, if what do I essentially see, that if I vary temperature with K with temperature, in case of paramagnetic minerals, I do see a curved something like this. Okay. Sometimes, you know, you can actually, so this is for ferro. Okay. And for paramagnetic, it is like this. Then you can essentially translate this curve as 1 by k, and then, of course, uh, versus t, and then this is how it looks like. Okay. For some particular minerals, that the paramagnetism actually starts after a particular temperature. Okay, after a particular temperature is achieved, then the paramagnetism actually kicks on. Okay, and this is what we call as theta, or paramagnetic Curie temperature. Okay, this theta is called paramagnetic Curie temperature. That is the temperature after which the paramagnetism essentially kicks on. This is k to the power minus 1 then. Okay, right. Now, in case of ferromagnetic minerals, there are kind of 4 varieties, if you like. So one is, it's not exactly varieties, it's like similar type of minerals. So one is ferro. In case of ferromagnetism, I see very strong alignment of magnetic moments. Hence, I see very high magnetization. Then there is something called antiferromagnetism. Antiferromagnetism means I have one directed very strong magnetic moment, but you know the consecutive magnetic moments are like oppositely directed. So the net magnetization still is 0 for a perfect antiferromagnetic mineral. Then you have something called spin centered ferromagnetic minerals. Sorry, spin centered and antiferromagnetism. And that is where, you know, it's not exactly perpendicular, but like you have a like a cycle that happens. Okay, and here it does have a magnetic moment, although not very high, but it will be oriented to a particular direction. And then something called ferrimagnetism. So this is called antiferromagnetism, antiferro. Then this is spin centered, and spin centered antiferromagnetism, antiferro. And then I have ferrimagnetism. In case of ferrimagnetism, of course, I have oppositely directed magnetic moments, but one of them is stronger, but the another one is like little bit feebler. Okay, and it does have a magnetic moment also. You know, in case of antiferromagnetism, I can see that the net magnetization is 0, but in case of ferrimagnetism, of course, there is a net magnetic moment. Okay, so I will stop it here, and tomorrow we will begin to discuss about few other things around basic rock magnetism, where talk about hysteresis loop, how it is applicable for us. We'll introduce you to something called anisotropy of magnetic susceptibility. Yeah, and then we will move on to other things on magnetism. If you have any question, sorry, I took a little more time of yours. Any question? All right, I think these were very much basics. You have already studied these things. The real fun and understanding that you will have to, you know, invest, that would be around your understanding of paleomagnetism and magnetic surveys. All right, so I will see you tomorrow. Thank you.